Consider this network simulation. Two AI agents are wired together, and one absorbs a dark payload. In the prompt infection study, researchers tested how well different models could withstand a prompt injection attack. GPT-4o consistently resisted initial intrusions that easily compromised the weaker GPT 3.5. However, that resistance created a higher threshold for damage. Once the security layer was breached, GPT-4o carried out the malicious instructions with high precision, far exceeding the impact the weaker model could achieve. When these models are placed into a multi-agent system sharing a single memory pool, individual capability flips from an asset to a liability. Your most advanced agent effectively becomes your most dangerous threat the second its context is poisoned. To understand why, we look at the state of the model itself. When an LLM is deployed on a task, its weights are frozen. The core algorithmic intelligence cannot adapt or learn mid-execution.
Because the model is static, the burden of coordination and the quality of teamwork falls entirely onto the data passing between the agents, the system's memory. The instant multiple agents read from and write to the same space simultaneously, that memory functions as a concurrent distributed communication protocol. Treating that space like a shared, editable document ignores the basic laws of distributed systems. It creates a direct contamination vector that exposes every agent to the errors of its peers. The architecture of multi-agent memory involves a permanent tension. Sharing context reduces handoff friction, while isolating context protects agents from one another. These three topologies dictate system safety. On the left, the shared store pattern utilizes a single core for all agents, maximizing context but offering zero containment. A fully shared store allows a hallucinated doc to immediately become absolute truth for every agent. In the middle, the private pattern enforces strict fault containment, with agents maintaining isolated scratchpads. On the far right, the hybrid setup. Raw reasoning scratchpads remain local, and only explicitly verified task events escalate to a shared global layer. Selecting a memory topology is a calculation of the system's blast radius. You decide exactly how many agents a single corrupted piece of data can infect. A common pitfall in system design is assuming agent memory functions like a mutable JSON object, where old data is simply erased and written over. Robust architectures, like the MetaGPT queue, utilize a steadily growing ledger. To maintain system integrity, multi-agent memory must function as an immutable append-only event stream, adding data sequentially without overwriting previous entries. The alternative, allowing agents to concurrently overwrite a shared state, creates a chaotic failure loop of erased data and mismatched context. An append-only log guarantees recoverable provenance, allowing developers to trace facts back to the specific agent that generated them, sidestepping concurrent overwrite conflicts. A shared bus with a durable history provides the mandatory coordination primitive required for agents to operate together without collapsing the system state. The risks escalate when agents share a vector database, represented here by millions of context points. The poisoned RAG study demonstrated injecting just 5 malicious texts into a database of millions yields a 90% attack success rate. The prompt injection self-replicates. Infected agents execute the malicious text and write outputs back into the shared pool. In the most dangerous variation, a compromised agent tampers with the memory importance score, artificially inflating the poisoned item's priority to ensure retrieval by others. Standard single-agent defenses are insufficient against this mechanism. Blocking it requires layered defensive strategies, such as semantic tagging, to verify the origin of retrieved text. When a shared vector store is the foundation of your architecture, a self-replicating contamination cascade becomes your primary threat model. If concurrent shared memory is inherently volatile, the question is how popular orchestration frameworks manage to function. Current frameworks survive by enforcing strict operational constraints that avoid concurrency altogether. Autogen, shown on the left, operates as a sequential group chat. This sequential activation relies on single-writer serialization, a constraint preventing data collisions by ensuring agents never write simultaneously. Attempts at concurrent resolution often utilize conflict-free replicated data types. CRDTs automatically merge updates for structured objects like task sets. However, free-form natural language prompts carrying semantic instructions cannot be mathematically merged. Sharing team state mid-run involves managing fragile, concurrent distributed state. Natural language memory behaves unpredictably, and does not function as a tidy, mergeable object. Looking at the entire multi-agent mesh, the individual nodes fade compared to the web of connections between them. Memory shifts from an attribute of the AI model into a functional action performed by the system itself. The behaviors we interpret as intelligent teamwork live in the wiring between the agents, defined by what is shared, what is partitioned, and what is permitted to cross a boundary. This wiring also creates the risk of artificial consensus within a poisoned network. 5 agents reading the same corrupted memory item provide zero independent verification. They represent a single compromised opinion multiplied by 5 inference passes. To build a secure system, keep raw reasoning local, share only validated coordination data, and treat every shared memory layer as a hostile retrieval surface. This returns us to the opening paradox of the highly capable agent. The more autonomous and capable an agent is, the more damage it can inflict the moment its memory is compromised. System resilience depends on the deliberate control of the blast radius when an agent fails, regardless of the raw intelligence within the nodes. When you build your next system, would you ship a shared, private, or hybrid memory architecture? And if you choose a hybrid model, what specific type of context would you absolutely never allow to cross into the shared layer? When multiple models run simultaneously, they are only as secure as the data they trade. The design of the memory topology dictates the ultimate safety and reliability of the entire system.